Okay, so let's do this one the regular way, meaning we're going to end up writing a function of two variables, and we're going to find the max or the min the usual way by finding the partials, finding the critical point, et cetera, et cetera, et cetera. So we're left with this, or we have, let's see, the problem says find the dimensions of the largest rectangular box by volume that can be mailed under the USPS requirement that the length plus the girth must be no more than 108 inches. Welcome, Josh. So let's see how our box looks. I'm just going to draw some kind of box. It's going to look like this. And as is typical, I'm going to call the bottom sides X and Y and the vertical side Z. Although you can label it however you want. And so we're going to say that the length is Z. And the girth is the around part. So the girth is going to be X plus Y plus X plus Y. So the girth is going to be 2X plus 2Y. Our job here is to maximize volume. Well, great. We know how to find the equation for volume. It's just the three dimensions multiplied together. So here, volume is equal to X times Y times Z. And you can see we're encountering the typical kind of problem in these maximization or minimization problems, which is that we want to maximize this thing, but the thing we're trying to maximize is a function of three variables. We don't know how to do that. So we're going to use this constraint to rewrite the equation as a function of just two variables. So we know that our length plus our girth needs to be less than or equal to 108 inches. Now let me ask all of you. If I'm trying to make the box that has the most volume, do I want my length plus my girth to be less than 108 inches? No, I want to use up all of the freedom I have and make my box exactly have a length plus a girth equal to 108 inches. All right, so that's what we're going to say. We're going to say our constraint is that Z plus 2X plus 2Y is actually equal to 108 inches. And then solving for any one of these variables, you can pick whichever one you want, but I'm going to pick Z because that means I won't have to divide both sides by 2. I'm going to get Z equal to 108 minus 2X minus 2Y. So very typically, if you're trying to maximize something that's a function of three variables, and we have some other constraint, we usually solve that constraint for one of the variables and then sub that back in over here. So now we can say that the volume as a function of just X and Y is going to be X times Y times 108 minus 2X minus 2Y. And although you might prefer to use the product rule, I don't. So I'm going to multiply that out before I start taking partial derivatives. So V of XY is equal to 108XY minus 2 times X squared times Y minus 2 times X times Y squared. A couple observations here. I will point out that this function is symmetric in X and Y, meaning if every X became Y and every Y became X, it would be the same function. That means I know that my answer, X and Y, are going to be the same value. It's a good thing to know, right? If you see that your function is symmetric in X and Y, it's a pretty good bet that X and Y are going to have to equal each other. Okay, so now we take our partials. Vx is going to be 108y minus, let's see, 4xy minus 2y squared. Set that equal to 0. And Vy is going to be very similar. It's going to be 108x minus 2x squared minus 4xy. Now this looks a little unwieldy, but what do you notice in this first equation that you could factor out from each of those three terms? Technically, there's two answers here that are both correct. What's one thing you can factor out from 108y, 4xy, and 2y squared? Right, definitely can factor out a 2. What else can I factor out? A y. So I'm left with 54 minus 2x minus y. So here's what I'm going to get. I'm either going to get y equals 0, which is probably not the right answer, because if y is 0, my box is not going to have the right volume. Or I'm going to get this part equal to 0. So that's going to give me 54 minus 2x minus y equal to 0, or y equal to 54 minus 2x. In the same sort of way, this other equation here, I can factor out an x. If I factor out an x, I'm going to have the same thing left over. Or sorry, factor out the 2x, I'm going to get 2x times 54 minus x minus 2y. 0. And now what I can do is they say, well, that also means I'm going to have 54 minus x minus 2y equal to 0. And now if I plug this in for y, I'll have an equation with just x in it. Plugging that in for y, I get 54 minus x minus 2 times 54 minus 2x equal to 0. Multiplying it all out, I've got 54 minus x minus 108 plus 4x equal to 0. 4x minus x is 3x. And 54 minus 108 is minus 54. And that's kind of tiny down there. 3x minus 54 equals 0, or x is equal to 54 divided by 3, which is 18. Correct. Because over here, sorry if you can't, I know, I got a little scrunched down there. I've got 54 minus x minus 108 plus 4x equals 0. 4x minus x is 3x. 54 minus 108 is minus 54. And then solving for x, we x equals 18.
And just swapping. I don't quite understand why, like, from the less than equal to 108, how it becomes 6.
Right. So we're trying to make the biggest box possible by volume. So if I want to make the largest box I possibly can, the length plus the girth could be less than 108. If I'm trying to make the box as large as possible, I want to use up all of the length plus girth I can. So I'm going to say, well, if I want to make this as big as possible, I know that the length plus girth should be equal to 108.
Like the maximum.
Right, exactly. Because let's say the length plus the girth was 100. Well, I could have made the box 8 inches longer and gotten more volume. Okay, so then if x is 18, we should end up getting y equal to 18 as well, and we do. If you plug that back in here, y equals 54 minus 2 times 18. 54 minus 36 is 18. And then going back over here, z is going to equal 108 minus 2 times 18 minus 2 times 18, which is going to be 108 minus 36 minus 36, which is going to equal 36. So z is 36 inches, y is 18 inches, and x is 18 inches. The biggest by volume box that you can ship through the mail is an 18 by 18 by 36 inch box, or 1.5 feet by 1.5 feet by 3 feet box. Kind of neat. I guess technically we should check to make sure that that's a maximum. Maybe this is a minimum. I doubt it, right? Because you could just make a box that's smaller. But let's check to see it's a maximum. So we'll go back up to the top here to write our work here. Is it actually a maximum? Well, let's see. Let's find Vxx and Vyy. So Vxx, looking down here, Vxx is going to be 0 minus 4y, minus 0. So our D is going to be minus 4y. That's Vxx. Vyy is going to be 0 minus 0 minus 4x. And then finally, Vxy is going to be, let's see, 108. Ooh, that's going to be kind of a lot. Vxy is going to be 108 minus 4x minus 4y. Yep, sorry, yes, of course. Apologies. Sorry, I forgot I zoomed in so much. So then if we plug in our critical point, which is y is 18 and x is 18, d of 18 comma 18 is going to be negative 4 times 18 is negative 72 times another negative 72 minus 108 minus 4 times 18 is 72 minus 72. And I forgot to square this here. All right, is this positive or negative? Ugh. That's pretty big. 72 times 72 is 4,900 something. 108 minus 72 is 36 minus another 72 is negative 36. So this is a negative 36 that's getting squared. This is a negative 72 that's getting squared. And since that's bigger, this whole thing is going to be positive. And then since your second derivatives are both negative, that means we're concave up, concave down, meaning we have a maximum. So yeah, sorry, excuse me. So yeah, we do have a maximum. Great. So now the whole reason we really talked about this example is so we can do it again, but now we're going to do it again in the context of LaGrange multipliers. Now it's kind of boring to do the same problem again, but it's worthwhile. So let's do the same thing. Same question. But now with LaGrange. Okay, so for LaGrange, we need to identify two things. We need to identify what we're trying to maximize or minimize. So here we want to maximize the volume, which is equal to x times y times z. I suppose I could draw the same picture again. And we also have to identify the constraint. The constraint is the fact that the length plus the girth has to equal 108. So that was that z plus 2x plus 2y equals 108. And I'm going to have to ask you all how exactly your professor does this. People do it slightly different ways. It doesn't actually matter, but I would like to be consistent with what the professor's doing. So typically the thing we're trying to maximize, we call capital F. So I'm going to call this, oh no, sorry, that's not true. I apologize, that's backwards. The thing we're trying to maximize, we call lowercase f typically. And the thing that's the constraint, we call lowercase g. Now, there's a couple ways of saying what g is. I like to just say that g is all the stuff that doesn't have the constant, but most professors, your professor probably did this. Correct me if I'm wrong, please. The professor probably said, I'm going to bring everything to one side. Let's write it more normally. 2x plus 2y plus z minus 108 equals 0. Does that sound like what he did? Yeah. So this here, that's what we're going to call g. And then we're going to define some new function. We're going to call it capital F of x, y, z, lambda. Or more generally, capital F of all your variables and then toss in a lambda. And that's going to equal lowercase f as a function of x, y, z minus lambda times lowercase g as a function of x, y, and z. That's the general idea. It is. So your new capital F function is just the thing you want to maximize minus lambda times the thing that you're constrained. And then here's what we're going to do. We're going to find all the partial derivatives of capital F. So I should say, in our example here, capital F of x, y, z, lambda is equal to x times y times z minus lambda times 2x plus 2y plus z minus 108. I ran out of room. It's terrible. Let me write that again. Sorry, one more time. F of x, y, z, lambda is equal to x times y times z minus lambda times 2x plus 2y plus z minus 108. So step one, step A, I guess, right? Find this capital F. It's just the thing you want to optimize minus lambda times your constraint. Part two, or part B, I guess, find all the partial derivatives with respect to x, y, z, and yes, even lambda. We'll talk about lambda in a second, because really you don't need that one, actually. So the partial with respect to x is going to be, well, if I take the partial with respect to f, x is going to be y times z minus this lambda is just going to hang out. And right, because it's a constant, and the derivative of this whole thing with respect to x is just 2. And we're going to set that equal to 0. And then we're going to do that for all the other ones. Fy is going to be x times z minus lambda times the partial derivative of this whole thing is also 2 with respect to y. And finally, fz is going to be, again, x times y minus lambda times just 1. And finally, now here's the thing you don't actually need to write, but you can if you want. I'm going to write it in red. F lambda is going to equal, well, the derivative of x, y, z with respect to lambda is just 0. And whatever you have here, there's not ever going to be any lambdas, it's always going to be 0. And the derivative of negative lambda times some stuff is just going to be -1 times that stuff. Here's what I want to point out. If you multiply both sides by -1, you just get 2x plus 2y plus z minus 108 equal to 0. Or if you prefer, 2x plus 2y plus z equal to 108. The thing I want you to see here, because I don't want you to waste your time writing f lambda, is that f lambda equal to 0 is just the constraint that we already had way up here. Literally the same equation is down here. Yeah, just I multiply both sides by -1, right? I can always multiply both sides by a constant. Yeah. So f lambda is just the constraint again. Or really I should say it's the constraint equal to 0, right? Okay. So now the job, and the job is kind of wonky. The job is essentially to, here's the way I think of it. You want to get 2 of your variables in terms of the third one. So I want to get like x in terms of y and z in terms of y. So then I can replace in my constraint x with a y thing and z with a y thing. So I have just all y's, and then I can solve for y. That is usually the process. People do this in different ways. Some people do a thing that I think is weird, which is where they divide this equation by that equation, which we can't really do right now because you got 0 on one side. Tell me your professor didn't do it that. You don't have to if it's a line, obviously. So let me point out what I think of as the standard way, but really here's the truth. There isn't a standard way of doing this. I'm going to show you what I usually do, which is I usually solve all of my equations for lambda. So I'm going to take this and say, okay, yz equals 2 times lambda, and then yz divided by 2 equals lambda. I'm going to take this equation and say xz equals 2 times lambda, xz divided by 2 equals lambda. And here, xy equals lambda. And then set any 2 of these lambdas equal to each other. So if we set these 2 equal to each other, we're going to get yz over 2 equals xz over 2. Multiply both sides by 2 and divide both sides by z to get just y equal to x. Right? Z over 2 is the same no matter what. So if these products are equal to each other, you have to have the x and y are equal to each other. And then let's use these 2 here. Let's set those 2 lambdas equal to each other. I get xz over 2 equal to xy. Again, divide out the x's on both sides. You're going to get z over 2 equal to y, or z equal to 2y. So based on what you've got, so actually I should back up for a second. Why didn't I just stop at y equal to z over 2? Well, in my equation up here, I have x equal to y or y equal to x. So I know I either want to write everything in terms of y or everything in terms of x. In this equation, I don't have an x. So I can't write everything in terms of x. So I have to write everything in terms of y. So I'm solving for everything in terms of y. So I'm solving for z in terms of y and x in terms of y. And I'm going to take these 2 things, I'm going to plug them back into my constraint. So my constraint was 2x plus 2y plus z equal to 108. And now I'm going to plug in x equal to y and z equal to 2y. So I'm going to get 2y plus 2y plus 2y equal to 108. Or 6y equal to 108, or y equal to 108 divided by 6, which is 18. And then if y equals 18, we're going to get x equal to 18. And if y equals 18, z is going to equal 2 times 18, which is 36, which is exactly the same numbers we got the first time we did it. The downside of this is there's not really a way of saying it's a max or a min. There is no way to test with LaGrange's method if you have a maximum or minimum. That's an unfortunate reality. There's nothing else you can really do about it. Okay. Questions so far? All right, let's do some more examples. Yeah. So this is the process so here's what I'll say. If someone says to find like maximize a function or like gives you a set of like find the volume find the maximum volume given that this constraint has to be true. Sometimes you can do it the first way we did it, and the usual way where you write it as a function of two variables and then find the partial, set them equal to 0, find the critical points, test what it is. And that's what I would generally do. If you can do that, I would say it's usually the easier way to go. However, sometimes you will be specifically asked to use LaGrange to do it. And so we definitely need to be aware of how to do that. So let's practice some more examples here. Let's look at the next example here. What do I got here? Let's find the dimensions. Yep, I was about to say I'm probably off screen here. Find the dimensions of the open rectangular box, meaning it doesn't have a top, with a volume of 32 cubic meters that has a minimum surface area. And although it's not absolutely required, I usually recommend drawing a picture. There's my open top box. Right, it doesn't have a top. Cool. And label the sides, typically X, Y, Z. And now we're going to first write what we're trying to maximize or minimize. Here we're trying to minimize the surface area. Minimize surface area. Well, great. The surface area is all the areas added up together. It's the bottom, which is X times Y, plus the front, which is X times Z, and the back, which is also X times Z, so 2X times Z. And then the left and the right sides are Y times Z twice, so you get 2 times Y times Z. And that is the thing we're trying to minimize or maximize or optimize. So that is our lowercase f. Our constraint, well, we're told that the volume needs to be 32 cubic meters. The volume equals 32 cubic meters, or X, Y, Z equals 32, or X, Y, Z minus 32 equals 0. I will point out, just because I can't not say it, it is actually totally fine to use either the thing minus the constant as your G, or just the thing without the constant as your G. Because the constant doesn't matter when we take the partial derivatives. So really you could use either one, but I will use the one that's similar to the way you're doing in class. Okay, so now we're going to set up capital F. In fact, why don't you all set up capital F? So I want you to write down what capital F of X, Y, Z, lambda should be.
There's your f of x, y, z.
It is. No, I don't recommend that. You can certainly, but it's easier really not to. Here's why. Lambda is a constant, right? You think lambda could be like 5. So when I start taking partial derivatives, so fx, well, the partial of this with respect to x is going to be y plus 2z plus 0. And the partial of this with respect to x, well, the minus lambda just hangs out. It's a constant multiple. And the partial derivative of all of this with respect to x is just going to be yz minus 0. So no, it's usually not worth the effort of multiplying lambda through. And then fy is going to be similar. It's going to be x plus 2z minus lambda times xz. And finally, fz is equal to 2x plus 2y minus lambda times xy. And you might notice I am not writing down f lambda because I know it's just the constraint. So eventually at some point, I'm going to go back and be like, I know I'm going to need to plug in x and y or whatever into this formula here. This here, that's our g, that's our constraint. That's what's right here. Oh yeah, yes. But you're right. That is exactly what f lambda would be, right? If we found capital F lambda, it would be exactly 0 plus 0 plus 0 minus 1 times xyz minus 32 equal to 0. And that's literally the same equation as that, just looking slightly different. So yeah, you certainly can write it down, and you should probably if your professor wants you to, but really you don't. All right, it's the same as before. We're going to solve for all the lambdas. There are other ways of doing this. I'm just doing it the way that's always worked the best for me. So solve for lambda. So I've got y plus 2z equal to lambda times yz. And then dividing by yz, we're going to get y plus 2z divided by yz equal to lambda. And here we're going to get the same thing except with x. You're going to get x plus 2z equal to lambda times xz. So you're going to get x plus 2z over xz equal to lambda. And then finally, the one that's kind of different, we're going to get 2x plus 2y equal to lambda xy. So 2x plus 2y divided by xy equals lambda. And then set any two equal to each other. Now, it's very kind of typical to set the first two together and the last two together because they're next to each other. That almost always results in getting things in terms of y. Let's do it slightly differently this time, just for the heck of making a different choice. So let's still set the first two equal to each other. We set those two equal to each other. I've got y plus 2z over yz equal to x plus 2z over xz. And you might be able to tell here that y and x have to equal each other. There is no way that they could be different. But if we want to do a little bit more work, do I really want to do more work? I really kind of do, yeah. You could, yeah, I kind of do. I guess we could cross multiply and say, great, xz times y plus xz times 2z is 2xz squared equals x times yz plus 2z times yz, which is 2yz squared. But then the xyz and the xyz cancel, and then you've got 2xz squared equals 2yz squared, and if you divide by 2z squared on both sides, you get x equal to y. And then just to change it up, let's set these two equal to each other. So now I'm going to have, okay, so, sorry, these two, apologies. I mean, they're the same ones, just, I'm actually using that. So I've got y plus 2z over yz equal to 2x plus 2y over xy. I, again, would probably cross multiply. I feel like that's the way to go here. So cross multiplying, xy times all that is going to be xy squared plus 2xyz equal to, on the right hand side, 2xyz plus 2y times yz is 2y squared z. The 2xyz's cancel. Then I have xy squared equal to 2y squared z. Well, I can divide both sides by y squared and get x equal to 2z. And I've done it again. I've gotten both equations in terms of one variable. Yeah. Well, what do you mean? It doesn't matter. But you basically, you can pick any two, and you can pick the one you didn't use in any one of the ones you already used. But you have to pick like 2 and then 2. And then, so notably, both my functions have, or sorry, both my equations have x in them. So I should be solving for the other variable in terms of x. So I should actually be writing this as z equal to x over 2. So then plugging both of those back into my constraint, I'm going to get, well, instead of x, y, z equal to 32, that was my constraint. Now I'm going to have x is 2z, y, oh, sorry, I did the wrong thing. I'm not plugging in for x, I'm plugging in for z. Apologize. So I have x times y, which is equal to x, times z, which is equal to x over 2 equal to 32. Multiply both sides by 2, and you've got x cubed equal to 2 times 32 is 64. You've got x equal to 4. If x equals 4, then y equals 4, and then z equals 4 over 2, which is 2. That is the box with the least amount of surface area that still has a volume of 32 cubic meters. Okay, so the process is kind of the same every time. Sometimes it gets a little weird, but most of the time it's find these partials, set them equal to 0, solve for lambda, set the lambdas equal to each other, and then get a relationship between x and y, or x and z, or y and x. Y and z, whatever, and then plug those all into the constraint. So you have just one variable in your constraint, solve for the thing, solve for the other things. Do I know it's actually a minimum? No, I don't. But it is. Right. Yes. Let's look at another example. Something a little more, slightly different. Back out here. All right, so here's the setup. Temperature. Yeah, it is a little blurry. Cool. Temperature on the ellipsoid, which is just like a 3-dimensional ellipse, x squared plus 2y squared plus 3z squared equal to 30 is given by the function t of x, y, z is equal to 2x minus y minus 3z. Find the hottest and coldest point on the ellipsoid. Points on the surface. Okay. So what are we trying to maximize here or minimize? Well, I'm trying to find the hottest point. I'm trying to maximize what? The temperature. So I want to maximize or minimize the temperature. So that's my F. And I want to have the constraint is that we are on the surface. Right? We're not talking about points that aren't on this ellipsoid. Our constraint is that we're on the surface. So our constraint is that x squared plus 2y squared plus 3z squared minus 30 equals 0. And we do the usual thing. So we're going to write capital F of x, y, z lambda is equal to 2x minus y minus 3z minus lambda times x squared plus 2y squared plus 3z squared minus 30. All right, I want all of you to find your three partials that matter. I want you all to find fx, fy, fz, set them equal to 0, and then solve each one for lambda. Let me give you a few minutes to work on that. Remember, you said going equal to 0. That's all for lambda. Right. It's a partial 2, and we have some minus up there. That's 2 minus, oh, that's 2x. Oh. Sure. So partial with respect to x here, what's the root of 2x going to be?
X.
Actually,
Oh,
the
two.
two, yeah. And then the partial here with respect to x, 2x times the negative lambda. I would say it's minus lambda. And then you're gonna multiply by 2x exactly, and that's equal to 0.
So when we, I'm just confused.
Sure.
What we're doing, like, we're solving the first area.
And we're not solving, we're differentiating, so we're using our partial derivatives just like we have been. Where we're just saying, okay, x is the variable, everything else is a constant. So what's the root of 2x? Excuse me, what's the root of y? Right, what's the root of 3z? Right, and here we have a constant multiple. So when you have a constant multiple, the multiple just kind of sticks around, just kind of like this 2 stuff around here. And you take the derivative of the inside part here. What's your x squared? Your 2y squared. Right, exactly. And there should be a plus 3z squared here as well. So, because you're also
This one. This one.
negative 1.
Oh,
Sorry. This. Went away, that's the worst. Yep, that looks right on. And good job. So now solve each thing for lambda. Not quite 4x though, right? Because now you're differentiating with respect to y. The root of 2y squared is going to be
oh, 4 X. Oh, 4y.
right.
Oh,
Mhm. That's a 3z squared there. Right, right, cool. Equals 0.
okay.
And now you're gonna wanna, what I would do usually is add this part to the other side. And then divide by whatever I need to, so I can isolate lambda.
Okay, okay.
Yeah, that looks. Excuse me, yep, looks right on, looks right on, it's all look right on. So now pick any two, set them equal to each other. And try and get, you're not trying to solve for, you're not trying to like get x equal to 2 or 3, you're trying to get x in terms of y or y. Yeah. Exactly. So the thing is, you don't need, so you can kind of, you actually almost. Oh, okay, so you set these two equal to each other, you got that. Right. So you actually only typically need two. Like, you don't need this last line at all. Over, right, because now you can say, all right, you can say that y equals x over -4 and z equals x over -2. Put it back in here, right? But you're plugging in 4y and 4z. You have to make a determinant of x. So you get it like y equals. Exactly.
It's X equal to -4y.
That sounds, yeah, x is minus 4y. Just to kind of point something out, which I think is weird, but other people totally like. Some people at this juncture here, instead of solving for lambda, do a funky thing where they divide this equation by that. And if you divided that, 2 divided by -1 is -2, and 2 lambda x divided by 4 lambda y would be 1/2 times x over y, and then you can get the same sort of relationship. I don't like doing it that way, but it is a valid way of doing it. So here, if we're going to solve, or if we're going to set things equal to each other, let's set these two equal to each other. You get 1 over x equal to negative 1 over 4y, or 4y equals to negative x. I'm not sure if I want to solve for x or y yet, so I'm going to leave it there for a second until I know what I want. And then I'm going to use these two. That's going to be negative 1 over 4y equal to negative 1 over 2z, or 2z, I guess negative 2z equals negative 4y. So now I can see that both equations have what variable in common? Y. So I'm going to write everything as solving for z in terms of y or x in terms of y. Right, whatever one is common, that's the one you need to write. You basically need to solve for the other ones. So here I'm going to say, great, x equals negative 4y. And here, z equals negative 4 divided by negative 2 is positive 2y. And then those are what I'm going to plug into my constraint. Now, you don't have to make the same choice. You'll still get the right answer if you get different things. This is just what I happen to do. So doing it this way, plugging those back into my constraint, I've got, okay, so x squared plus 2y squared plus 3z squared equal to 30 is going to become negative 4y squared plus 2y squared plus 3 times 2y squared equal to 30. I got to solve this here. So let's see, 4 squared is 16y squared plus 2y squared plus 2 squared is 4, and 4 times 3 is 12y squared equals 30. 16 plus 2 plus 12 happens to be 30. So I end up getting 30y squared equals 30, or y squared equals 1. So y equals plus or minus 1. And it makes sense that there's two answers because there should be 2 points, a hottest and a coldest. So then finding my other points, y equals plus or minus 1, x is going to equal negative 4 times plus or minus 1. So minus plus 4, and z is going to equal 2 times plus or minus 1, so plus or minus 2. So my points are negative 4, positive 1, positive 2, and positive 4, negative 1, negative 2. Question, Justin? It just means that there's 2 solutions. Oh, so the reason I wrote minus plus here is to kind of point out the fact that if y is positive, x is negative. And if y is negative, x is positive. Well, hold on, Justin. It only matters in that if you've got more than one thing, right? So if I could have written this out as the 2 points minus plus 4 plus or minus 1 plus or minus 2. And that really indicates that it's minus 4 plus 1 plus 2 and plus 4 minus 1 minus 2. Yeah. Let's see. No, let's see. I'm not sure. Let's take a look. So z and y are the same sign. Z is equal to 2 times y. So if y is plus minus, z should also be plus minus. That would be incorrect. That is not a point because if y is 1, then x is negative 4 because x is equal to negative 4 times y. I really have to sneeze. Really. The worst. So terrible. I really want to sneeze so badly. Anyway, to wrap it up, we still have to figure out which one's the hottest and which one's the coldest. So we're going to plug back into the temperature equation and say, okay, well, the temperature at 4, negative 1, negative 2 is going to be 2 times 4 minus negative 1 minus 3 times negative 2, which is going to be 8 plus 1 plus 6, which is 15 degrees Celsius. I don't know what the units were. No one said any units. And the other temperature at negative 4, positive 1, positive 2 is going to be the opposite sign, right? It's going to be 2 times negative 4 minus 1 times 1 minus 3 times 2, which is going to be negative 8 minus 1 minus 6, which is negative 15. So here is our maximum temperature. And here is our minimum temperature. All right, 159 stuff. So just as a reminder, I said this before, but I'll say it again. We will not have this co-class on Friday and Monday because I will be out of town, but I do plan on trying to make a video covering what you're going to go over next, which I think is going to be double intervals. So I will make a video talking about that. Also,